Today, we're looking at section 1.3, and section 1.3 is about experimental design. When you want to conduct a statistical investigation, you must collect data. The way you collect the data is as important as the data itself. And if you have any flaw in the data collection process, then that invalidates the results. No matter how much good work you've done, if you have messed up that process in any way, then that data is all worthless. So it's very important that when you're designing an experiment, that you are very careful about how you go about it, because even the slightest flaw will cause people not to accept your results. So we always want to maintain 3 features in any well-designed experiment. Those 3 features are control, randomization, and replication. So we're going to talk about these in order. We'll start with control. Control is the ability to eliminate or reduce the effects of outside influences on data collection. The ability to eliminate or reduce the effects of outside influences on data collection. How is that possible? It's definitely not easy, and sometimes outside influences do still get in the way. So here's another concept, the concept of the confounding variable. So a confounding variable is when an outside influence makes it impossible to determine what caused a particular result. So let's look at an example. A man develops a chronic cough shortly after his wife buys a new dog. He goes to the doctor and is given a prescription. After a couple of days, his wife decides to give the dog away because it chewed up her best shoes and purse. The man's cough clears up. So the question we ask ourselves is, what caused the result? Was it the prescription that the man got from the doctor? Was it effective against whatever his coughing issue was? Was it the removal of the dog? Did the man happen to be allergic to the dog, and that was what was causing his cough? And so when you take the dog away, the cough goes away? And the answer here is we just don't know. So this is the idea behind the confounding variable, because we can't be certain what caused the cough to go away. If all that had happened was the removal of the dog and the cough went away, then we would feel better about thinking that the cough was being caused by the dog. If the only change that we made was taking the prescription and the cough went away, then we would feel very confident about the prescription being the cause of the cough going away. But because 2 things happened, removing the dog and taking a prescription, we're not sure which one caused that effect. We're always looking for a cause and effect relationship, and if there's too many potential causes, then we can never figure out that cause and effect relationship. So this idea of a prescription brings us to our next statement, and that is that one field in which statistical investigations are frequently performed is the field of medical research. And we use statistical investigations to test new drugs and treatments after they're developed. In most new pharmaceutical testing, there are 2 groups of subjects. You may have heard of these terms before. We have the test group, and the test group is the individuals who are actually receiving the new drug or treatment. And then the second group are the control group, and those are individuals who are not receiving the new drug or treatment. The thing is, though, they are receiving something. So for instance, if we're giving everybody a pill in the test group, we're also giving everybody in the control group a pill. So they're going to receive a pill that looks identical to the drug that's being tested. That pill that they're going to get is only a sugar pill. And this helps determine the influence of the placebo effect. So what is the placebo effect? Well, it's a phenomenon where patients who are receiving a placebo, which is a fake drug, show improvement as if they were taking an actual drug. It's generally attributed to the power of positive thinking. The human mind is an amazing thing. If you give somebody a pill and tell them that it's for a particular condition, say you give the man a pill for a cough, and that is just a sugar pill, if he believes it will help his cough, it's possible that it does. The human mind's capacity to help heal your body is astounding. So if people really believe that they're getting treated for something, oftentimes they improve, even though that treatment is not real. It's just a sugar pill. When you're doing medical research, pharmaceutical research, you want to be able to see if there's a significant difference between taking the actual drug and taking a sugar pill. Because if there's not a significant difference in improvement between the placebo and the real drug, then why take the real drug? Just give the person a sugar pill and call it a day. If you ever watch television and see an ad for a new pharmaceutical product, they list side effects that a lot of which sound very dangerous. You know, you hear about heart conditions and allergic reactions, swelling of the tongue, swelling of the throat, difficulty breathing, all these different kinds of side effects that could be life-threatening. If you're not getting any good benefit out of taking that pill as opposed to taking a sugar pill, then don't ever take that medicine. So when you're doing a statistical study, you're trying to show that there's a significant difference between taking a sugar pill and taking this treatment. Because if there's not, the side effects aren't worth it. Okay. So if you have a control group and a test group, it is important that the members of those groups don't know to which group they belong. Why? Why is it the case that we want to keep them in the dark? Why don't we want to let them know what group they're in? The answer is, if a person knows he or she is receiving the drug, then that person might believe and report improvements when there aren't any. So we want to make sure they don't know. We want them to know there's a test group and a control group. Some of you will receive the real medicine, some of you will receive a fake medicine. That way they can't automatically believe that they're receiving the treatment. And so the results that happen are more likely to be attributed to the drug. If somebody knows that they're in the control group, which means they're not getting the drug, they may not report improvements that do occur. So if I'm in the control group and you give me a fake pill, but I start feeling better, I might not tell you that I'm feeling better because I don't think I should be. Remember, a lot of the research that goes on is question and answer between the researcher. How do you feel today? What symptoms are you having? When you see those commercials on TV for drugs and they list all these side effects, the reason that you see all these side effects is because during the process, when the researchers were sitting down with the individual patients and asking them, how are you doing today? Do you have any symptoms? Are you feeling any different today than you are yesterday? Can you detail these things for us? Well, if, let's say, today you have a massive headache, doctor, I have a bad headache. They write that down as part of their research. And because that happened during the study, the FDA, Food and Drug Administration, requires them to report that out. So that makes it to the list of potential side effects. The headache may not have anything to do with the medication itself, but they still have to list it as a potential side effect. Now, if 30 subjects come and say that they had headaches, then that's more likely to have come from the drug that they're taking. So you'll oftentimes see in those commercials, it'll say more frequent side effects include, blah, 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 and less frequent side effects include. So if you get a lot of test subjects that have a particular symptom, then that's more frequent. If it's just one or two, then that's less frequent. But they all have to be listed. If you get a brand new medication, or if you get any medication really, they're supposed to include with it this gigantic insert that tells you all the different potential side effects of the drug. And some of those lists are massive. So always be aware of that. That's statistics. That's statistics at work. So this leads us to some new concepts. The first is the concept of blinding. In a blinded experiment, that's when none of the test subjects know whether each is receiving a treatment or a placebo. That's how we want to run our experiments. We want to make sure that none of the test subjects know whether each is receiving a treatment or a placebo. Then there's the concept of double blinding. In double blinding, that's when neither the test subjects nor the researchers know who is receiving a treatment or a placebo. So how would that work? How could you possibly run an experiment where neither the test subjects nor the researchers know who is receiving a treatment or a placebo? How do you make sure that the test subjects are receiving the real drug every day and that the control group are receiving the placebos every day if the researchers don't know who's in what group? Think about that for a second. How would you do it? And the answer is there has to be a third party involved. In these research experiments, they'll contract with an independent third party who will administer all the drugs. So they'll take the test group, they'll take the control group, each individual is assigned a number, and then based on that grouping, they know which numbers are in the test group, which numbers are in the control group, and they'll take little cups that have those numbers on them, and every morning or 3 times a day or however often this pill is supposed to be taken, they will get those cups and they'll put the correct pill in each cup, whether it's the placebo or the actual drug, and then they have a nurse or an attendant that passes out the medication to the correct person by those numbers. And then that way they're either always getting the fake pill or they're always getting the real pill. But the researchers themselves don't have any idea who's getting what drug because, again, these drugs are identical. The fake pill and the real pill look the same. So all they see is the patient taking the medication. So they don't know who's in what group, and the people don't know what group they're in. So that's a double-blinded experiment. So most medical research studies are double-blind studies. We always want to try to keep both sides in the dark. The reason we want to keep the researchers in the dark is really the same reason we want to keep the patients in the dark. Researchers are people too. And if I have a new drug that I've developed and I really want to know if that's going to be effective, then my own personal opinion about whether or not it should be effective might color my judgment when I am looking at my patients. Because when I'm talking to my patients and asking them questions, not only am I relying on their responses, but I'm relying on my own observations, right? What do I see when I'm looking at that patient? Do I see that they look tired? Do I see that their skin tone is pale? Do I notice that they are sweating a lot? Do I see any physical characteristics that are different from yesterday? So if I know that they're in the test group, I might report things because I believe that those things are being caused by the medicine. Whereas if I know that they're in the control group, then I wouldn't report those things because it wouldn't matter. And that's not fair to the experiment. So you have to report everything without any kind of coloring of your own opinion. And that coloring is called bias. We'll talk about bias later in this section. So let's move on to the next concept. Remember, we said that there were 3: control, randomization, and replication. So the next concept is randomization. Randomization is the process of randomly assigning subjects to different test groups, either the test group or the control group. Now, this is an important idea, but the manner in which you go about it is equally as important. So let's talk about a completely randomized design. This is a process by which subjects are assigned to different test groups through random selection. And the thing you have to know is that this is not always the best idea, and that it might lead to wildly dissimilar test groups. Why would that be the case? You would think that complete randomness is the best, because if there's any lack of randomness, then we might not get valid test results. But in fact, too much randomness causes a problem. Let's see an example. So a group of 100 individuals, 50 men and 50 women, are chosen to test a new medication. They'll be split into a test group and a control group using a completely randomized design. The result of the random assignment is shown below. So we let a computer-generated process pick out 50 of these individuals to be in the test group, and the other 50 will be in the control group. And so by letting it be completely random, this is the result we got. The test group consisted of 47 women and 3 men. The control group consisted of 3 women and 47 men. So what might be some problems with that design? Well, if you're testing a new drug, and that drug interacts differently with estrogen than it does with testosterone, this could be an issue, because women have much higher levels of estrogen than men do. Men do have some estrogen in their bodies, but not at the levels that women have. So if the drug interacts in a certain way with high levels of estrogen, then it's going to act differently on women than it does on men. In the same way, if it reacts with high levels of testosterone, then it's going to react differently with men than it does with women. So having test groups that are randomly chosen might lead to a whole lot of women in one group and very few men, and a whole lot of men in the other group and very few women, and that might throw off your results. So, what might be a better way to choose this group? Because if we let it be completely random, this is a possible group. It would also be possible to get all 50 women in one group and all 50 men in the other group. Not likely, but possible. And if we're letting it be completely random, then any of those possibilities could happen. So what would be a better way to go about this? And the answer is a randomized block design. So this is a process by which subjects are divided into groups with similar characteristics, and then you randomly assign half of the members from each characteristic group to the test group and the other half to the control group. And what this does is it ensures similar test groups. So, thinking back to that last example, what would have been better is if we had said, here's our 50 men, here's our 50 women, let's randomly assign half of the men to the test group, and let's randomly assign half of the women to the test group, and then that way our test group would be made up of 25 men and 25 women, and our control group would be made up of 25 men and 25 women. But they would still be randomly chosen. It's just not completely random, because we're not letting every possible group happen. We're only letting the possible groups that have 25 men and 25 women happen. So we haven't lost our randomness, we've just lost complete randomness. So that's randomization. The next concept is replication. So what is replication? Well, replication is repeating an experiment with a large number of test subjects. You never just want to do a drug study with one person or 2 people. Some people have peculiarities in their bodies that cause them to react differently than the average person would from certain stimuli. So you give people a medication and they react differently. Myself, I have a very strange reaction when I take Demerol. If you're familiar with the drug Demerol, it's a depressant. It's used as a hospital pain reliever. It's the kind of thing they give you by injection, and within seconds you're out of it. When I was given Demerol, I get hyperactive and my heart starts racing It does exactly the opposite thing that it's supposed to do. It's supposed to calm people down, make them drowsy, put them to sleep, take the pain away. That's not what it does for me. It does something completely different. So if you had a research study with one person and they happen to react in a peculiar manner to whatever it was that you were testing, then that might not give you accurate results. You want to make sure that you have a sample of individuals instead of just one individual. And a small number of subjects can greatly skew the results. Imagine if you had just one person or just two people and one of them had a heart attack. The heart attack might not have anything to do with the drug that you're taking, but then you'd have to say, well, we just had the one person in the study and they had a heart attack, so this drug causes heart attacks. But if you had 1,000 people in the study and one person had a heart attack, you'd still have to list heart attack as a potential side effect, but you would say that it was not very frequent. So those results from the test could be greatly skewed by having too few individuals. So, now we want to talk about one of the most important concepts in the study of statistics: data collection. Remember what we said at the beginning. A flaw in your data collection process can invalidate the entire statistical study. So there's lots of methods by which you can obtain data. We're going to detail a few of them here. Our first data collection method is a census. So what's a census? We've actually talked about this back in section 1.1. A census is a count or measure of every member in a population. Now, that's not easy to do. It's problematic with large populations. Every 10 years in the United States, we're required to have a census, and you're supposed to count everybody in the population. Well, there's upwards of 330 million people in the United States. So how do you make sure that you count them all? And not only that, once you've done a count, if you could count everybody on one day, the next day, that count would be off, because new babies are born every day and people pass away every day. So that number is in flux. It's constantly changing. Some days it's going up, some days it's going down, and we don't know exactly where it is at any given time. It's also expensive. The federal government pays billions and billions of dollars to perform the census, because you have to have the paperwork that people fill out. They're doing more of it online now, but there's still paper copies that go out. They hire people to go door to door to ask questions when they don't get responses from households. That's a very dangerous job, by the way, because if people don't answer the census, sometimes it's because they don't want to be found. And if you go try to find them, they're not happy about it. You also have to hire people to compile the data. You have to hire companies to develop the software to tabulate everything. There's just a massive amount of expense in performing a census. Now, if your population's very small, it's not an issue, right? If you have a population of 30, it's not a big deal. If you have a population of 330 million, now it's a big deal. The next data collection method is going to be a simulation. And I always laugh because people will say stimulation when they write answers on exams. It's not stimulation, it's simulation. And what a simulation is it's a physical or mathematical model used to reproduce the conditions of a situation or process. Now, these models that we use are often computer generated, and they allow you to study things that are dangerous or impractical to investigate. So for instance, let's say you were a volcanologist. A volcanologist is a scientist that studies volcanoes. And you were studying a particular volcano that was active, wasn't currently erupting, but it definitely could soon, and you wanted to get some readings from the magma chamber. Well, you don't want to go down there yourself, because honestly, it could erupt at any time. The last place you want to be during an eruption is in the magma chamber, because that's where all the action is. So you might send some remote drone down there to gather data, and then from the data that you obtain, you can build a mathematical model that shows you how it's reacting, and it can also help you make predictions. You wouldn't want to be the one to go down there. You would want to actually get some kind of data. You don't want to just watch it happen because you want to be able to make a prediction. You want to say, hey, we need to evacuate the residents of this town that's close to this volcano because it's going to erupt in the next 2 days based on the model, right? If you just wait and watch and see, then you don't have enough lead time to help save people's lives. So you definitely want to have some kind of a model, which is a simulation, to help you decide how things are going to happen. So let's move to the next data collection method, which is an experiment. What an experiment is it's when a treatment is applied to a part of the population and responses are observed. So again, when we have a medical experiment for pharmaceuticals and we have a test group and a control group, that's part of the population that's getting the treatment. That's an experiment. But in statistics, we frequently use another method for gathering data. And the method that we use is called sampling. Now what sampling is it's a count or measure of a portion of a population. So it's like a census. A census is a count or measure of every member of a population. It's just that we're counting or measuring a smaller portion. It's much easier to do than a census, right? We could have a sample of 10,000 individuals for people who live in the United States instead of 330 million. And a 10,000 person sample is much easier to work with than a sample with 330 million people. If you do it the right way, though, you can take those results and extrapolate them to the population as a whole. So if your sample is what's called a representative sample, if it well represents the population. So let's say you took a sample of 10,000 individuals from the population of the United States. And when you looked at your sample, that sample had 10,000 white males in it. That would not be a representative sample because it's missing every other ethnicity and it's missing every woman in the population. You need to have representation from every portion of the population for you to be able to have a representative sample, because we want to be able to extrapolate those answers that we get from the sample to the population as a whole. But if the sample doesn't represent the population as a whole, then we can't make those kinds of jumps. And there's lots of different sampling techniques that we'll encounter, and we'll detail a few of them here. The first is called a random sample. And a random sample is when every member of a population has an equal chance of being chosen. The next one is called a simple random sample. And a simple random sample is when every possible sample of the same size has an equal chance of being chosen. So what's the difference between a random sample and a simple random sample? They seem very much the same, because in a random sample, every member of the population has an equal chance of being chosen. In a simple random sample, every possible sample of the same size has an equal chance of being chosen. If every sample of the same size has an equal chance of being chosen, then that means that every member of the population has an equal chance of being chosen. So why is a simple random sample any different than a random sample? And the answer goes back to that example that we did, where we had the 50 men and the 50 women, and we let a computer randomly select 50 individuals for a sample group, and we got 47 women and 3 men and 47 men and 3 women as our groups. In a simple random sample, that group could happen, because in a simple random sample, every possible sample of the same size has an equal chance of being chosen. So the group with 47 women and 3 men would have an equal chance of being chosen. We don't want that. It's the simple random sample that makes that happen, because everything is fair game in a simple random sample. The random sample just means that every member of the population has an equal chance of being chosen, not that every group has an equal chance. So when we did that sample and we made the adjustment and we said, well, we're going to take 25 men and 25 women, Now, every member of the population still has an opportunity to be chosen, but not every group can be chosen, because the group with 47 women and 3 men is no longer eligible. But each man and each woman has an equal chance of being chosen. So that's the difference between those two. In a simple random sample, anything goes as far as the makeup of your sample. Whereas in a random sample, there might be additional requirements to be in the sample that don't preclude each individual from having an equal chance, but they do preclude certain groups from having a chance. So it's a small distinction, but definitely one worth mentioning. We often want to use a random number generator, and the TI-83, TI-84 graphing calculators have random number generators built in. So let's see how we would use that function on the calculator. Here's an example. There are 1,739 students enrolled at the Madera Center. The administration wants to select a random sample of 30 students to survey about campus security. Use the random integer generator on your calculator to select the students in the sample. So here's our solution. First, we would assign each student a unique number from 1 to 1739. So that's student 1, student 2, student 3, however we do it. They don't have to be alphabetical, just as long as each student has their own individual number from 1 to 1739. Then we're going to turn to the calculator. So from the home screen, which is the screen that's present when you turn on your calculator, you press the math button, and you should see this. It'll have math across the top along with num, CPX, PRB, and several options below. You're going to want to move over to where it says PRB. So use your navigator keys, which are the arrows at the top right of your keypad, to move the highlight from math to PRB. That's probability screen. And you should see this screen when you do that. So when PRB is highlighted, you see that the choices in the menu have changed. And you're going to want to scroll down to where it says randint. That means random integer. So you scroll down until that's highlighted, and then you're going to press enter. And then on your home screen, it'll type in randint. Now we have to tell it the parameters. Where do we want it to find these random integers? So you'll type these numbers, 1, 1739, 30. So what does that mean? Well, the first two numbers give the calculator the range where it's looking for the values. So we're telling it to look for numbers randomly between 1 and 1739. The last number after the comma tells it how many of those numbers we want. So it says find 30 of those numbers. So we tell it look from 1 to 1739 and randomly select 30 of those numbers. If I press enter, it'll generate a list for me. And your list on your calculator might be different than this, but it will generate a random list of numbers between 1 and 1739. So that ... means that if you press the right arrow key, you can scroll through all the values and see them all. Because it can't list them all on the screen, that allows you to see them all in your list. So now we want to look more deeply at sampling techniques, because there are several different sampling techniques that we'll encounter. Some of them are more appropriate to certain situations than others, and we want to learn about the different features of those sampling techniques so that we can know which one to use in each individual circumstance. So we're going to start with a stratified sample. What a stratified sample is where members of a population are divided into 2 or more subsets that share a common characteristic. Each subset is called a stratum. So stratum is singular, strata is plural. Characteristics are things like age, gender, religion, ethnicity, political party, level of education, level of income. It could be personal interests. Lots of things can be your strata and how you define things. And what you do is you're going to choose a random sample from each stratum. So let's say you're taking a political survey and you want to know how people feel about a particular issue. Well, you don't want to just ask Republicans. You don't want to just ask Democrats. You don't want to just ask independents. So what you do is you break up your population along different party lines, and you make sure that you've got a sample from each one of those levels, from each one of those strata. Right? I want to make sure I've got some Democrats. I want to make sure I've got some Republicans. I want to make sure I've got some independents, to make sure that my sample is representative of the population. So that's what a stratified sample is where we break down the population based on a certain characteristic first, and then we take a random sample from within each one of those to form our random sample. The next one is called a systematic sample. In a systematic sample, members of a population are assigned a sequential number. A starting number is chosen at random, and from that point, you choose every 4th or 7th or 33rd or etc. number to create your sample. Your spacing is up to you, but you must remain constant throughout the process. So in other words, once you've chosen what your spacing is going to be, so let's say you decide, I want to pick every 10th person. You have to do every 10th person all the way along. You can't choose every 10th person and then all of a sudden somewhere along the way switch and say, I'm going to do every 13th person now. The spacing has to stay the same the entire time. So you should really choose the spacing before you choose that starting number, because you might be accused of trying to make sure that an individual is chosen as part of the sample. For instance, let's say that I want to make sure that person number 45 gets in the sample, and then I randomly select the number 7 as my starting point. Well, if I randomly select number 7, then I might say, okay, well, I'm going to do every 19th person now. So that it goes 7, and then 7 plus 19 is 26, and 26 plus 19 is 45. And now I've made sure that person 45 gets in there. We don't want to be accused of that. So if we choose our spacing first, and we say, okay, I'm going to do every 19th person, and then you randomly select 11, well, now the chips fall as they may. So having that spacing set before you choose your initial starting point is an important way to help eliminate bias from your sample. Our next sampling technique is called a cluster sample. In a cluster sample, the population naturally falls into subgroups. The word naturally might be a little bit misleading here, because it might not be nature that's creating those subgroups. It might be human beings. But the idea is that those groups exist before we start our study. So they are pre-existing groups from which we will get our sample. How does that work? Well, it could be cities, it could be counties, zip codes, offices, classrooms that we use to form our sample. So for instance, every couple semesters we'll have to give a survey on campus. And they'll choose a certain number of classrooms and say, okay, in this classroom at this time, we want to survey all the individuals in that room. And in that classroom at that time, we want to survey all the individuals in that room. They don't survey everybody, but what they do is they pick out 20 classrooms at certain times, and they say, we're going to survey all of those 20 classrooms. And each one of those classrooms is a cluster. The clusters must have similar characteristics to be valid, and you're going to randomly choose some, but not all of the clusters to gather your data. So if you're using classrooms, and let's say there's 143 classrooms, and you choose 29 of them, that would be appropriate, right? You would choose some, but not all of those clusters. Then we have a convenience sample, and a convenience sample is pretty much the sample that students take if you're given a project to do in statistics. So it's a sampling technique by which you choose only readily available members of the population. Think about it. If I gave you an assignment and I said, I want you to go ask 10 people these 3 survey questions, how do you do it? Do you go and stand on a street corner and wait for 10 people to walk by? No, you don't do that. Do you get a list of all the students at the Madera Center and use a random number generator to figure out 10 of those individuals? Nope, that's not what you do. What you do is you ask 10 people that you know, your friends, your family members, whoever is readily available, and you ask them those questions. The problem is that method sucks. It easily leads to bias. How does it lead to bias? So let's say all you did was choose 10 of your friends. Why would that be a problem? Well, people choose their friends oftentimes based on having something in common. And if you have a group of people and you all have something in common, then you might think the same way about different topics. Let's say it was a political question in the survey. A lot of times you don't see people who have very liberal views and very conservative views that are friends. Sometimes you do. But oftentimes, people who have very liberal views will associate with other people that share those same political views, and people with very conservative political views will associate themselves with other people with very conservative political views. So if you're just taking a sample of friends, it might be that they all feel the same way, which is not necessarily representative of the population as a whole. So that's how it can easily lead to bias, because you're picking similar individuals and not a cross-section of the population. So we need to define what bias is. What is bias? Bias is any factor that may skew the results of a statistical investigation. So how can bias occur? So I want to look at an example as we're doing this, and it's not on the slides, it's just going to be a verbal example. So let's say I give you a project, and I say, I want you to form a survey and go give this survey to 50 people. And you're just going to ask them one question, and the question is completely up to you. You get to decide what the question is. But before you do that, before you go and give this survey, you have to come by my office and talk to me about your survey question so that I can make sure that you've got a good question. All right? I just want to know that you're asking a good question, something that you're going to get good results for, or that might be interesting to investigate. So you think long and hard, and you come to my office. You say, Mr. Kandarian, I have my topic. And I say, okay, so what is your survey question? And you say, I wanna ask people about abortion. And I say, okay, what do you want to ask? So the question that you decide to ask is, do you believe that it's okay for women to murder unborn innocent children before they've had a chance to live a rich, full life? And I look at you and my mouth falls open and I say, you can't ask that question. Because one of the ways that bias can occur is the way in which a question is asked. In that question, you're assuming that abortion is murder. Abortion is legal. Now, you may have an opinion. You may think that it's murder, but that doesn't mean that it is murder. That doesn't mean that there's anything wrong with having an abortion. It's your personal opinion. But the way that you've asked the question, you've inserted your own personal opinion about whether or not abortion is right or wrong. You've called it murder. How many people, if you ask them, do you think it's okay to murder babies, are going to say yes? It's not very likely. But that's because you've called abortion murder. Now, you may believe it is, you may believe it's not. Those are your personal opinions. I'm not making any statement in this class about whether I think it's right or wrong. What I am saying is, in a valid statistical survey, you couldn't ask a question like that. It's what's called a loaded question. You've put in all kinds of preconceptions into the question itself that are going to lead people to either agree with you because they believe that abortion is murder, or they won't answer truthfully because they don't want to be judged as being a baby murderer. So you can't ask loaded questions. Your question has to be very antiseptic. It has to be very benign. So I tell you, I say, you can't ask that question. It's too loaded. I want you to go and rewrite the question and make it a better question. And you say, okay. So you come back to my office a few minutes later. You say, okay, Mr. Kandarian, I rewrote my question. Say, all right, lay it on me. What's your new question? My new question is, do you believe that it is a woman's right to have an abortion? And I say, okay, that's a valid question, because you're just asking the question, do you believe it's a woman's right? You're not loading it with baby murder things. You're just asking, do you believe that it's a woman's right? And a person could feel free to answer yes or answer no. So I say, okay, go out and do your survey. So you come back to me the next week and you say, Mr. Kandarian, I did my survey. And I say, okay, well, how did you do your survey so that I can let you know if, you formed a valid survey? And you said, well, I decided I needed a large group of people because I wanted to ask a lot of people this survey question. I said, okay. So what I did is I went to St. Joachim's Catholic Church on Sunday morning as Mass was letting out, because I knew there would be a lot of people there. And I asked them the question, do you believe that a woman has a right to have an abortion? And I got a lot of responses. And you know what, Mr. Kandarian? A lot of people said no. I was surprised at how many people said no. And then I, of course, am sitting there at my desk with my mouth wide open, all agape. And I say, that's not a good sample, because bias can also happen in the way in which a sample is chosen. So here you're asking this question about abortion, and you go to a Catholic church. Now, Catholic churches are well known for being anti-abortion. So you've skewed your sample. Does that mean that all Catholics are anti-abortion? No. But as a whole, Catholicism is anti-abortion. So you're going to get a heavily skewed sample that shows that most of those people are going to say, no, I don't support abortion. That's not a valid sample, though, because it doesn't take differing opinions into consideration. You've skewed the sample by choosing a bunch of people who are going to pretty much answer the same way. So I say you can't have that survey. You can't ask those people. You could go there and get some, but you can't make that your entire set of individuals that you're sampling. So I tell you, no, you can't do it that way. You have to go and redo your sample. You say, okay. So you come back to me the next week and you say, Mr. Kandarian, I redid it. I went to the office and I had them generate a bunch of student ID numbers randomly, and then I contacted those students and asked them the question. And I said, okay, that's fine. That's great. There's randomness in there. You're not presupposing the answer when you ask the question. I said, well, what were your results? And you say, well, 51% of students support a woman's right to have an abortion. 49% of students don't. I said, well, what's your interpretation? You say, well, a vast majority of people support a woman's right to have an abortion. And I look at you, and my mouth is hanging open again. Because 51 to 49, that's not a vast majority. So what you'll see is that bias can also occur in the way in which the results are interpreted. Sometimes you have researchers whose results are just whatever, but they make a big deal out of them, even though they're not that significant. So there are lots of different ways that bias can occur. It can occur in the way in which you ask a question. It can happen in the way in which you choose your sample. It can happen in the way in which you interpret your results. But whatever you do, avoid bias at all costs. Bias will mess it all up. That's one of those things that can definitely invalidate a study. So that brings us to an end of section 1.3. Please look on the Pearson website for your homework, and have a great day.